Session 5A, I'm sorry, session 5B. Got to get in the right room here. Session 5B, we're in Kiva B on resource adequacy, a hot topic. And Bethany will probably say something about the resource adequacy report that ESIG released last week. I think the third in the series. It's another, I think, very interesting one. So Bethany Frew from NREL is going to be chairing the session. Bethany is a member of our board and a member of our offerings committee or meetings committee. So if you have any complaints about the parallel sessions that we're running here, you'll have to speak to Bethany. Okay, Bethany, I'm going to turn it over to you.
Thanks, Charlie. All right, well, thanks everyone for joining. I know it's getting later in the day and energy levels may be waning a bit, so hopefully we'll keep things exciting here for the last 2 hours. So this is a little bit of a longer session, but after this you get happy hour, so just hang on. I'm going to try to keep the energy up in this session. So this is all about resource adequacy, and despite the very simple title, I think the presentations today will be anything but simple. For those of you who have been engaged in some of the discussions around resource adequacy, this has been a really hot topic lately. There is a growing awareness that we need to improve our methods, our metrics, the data that goes into the tools that are being used. All of that is really to reflect the need for addressing greater complexity, greater uncertainty in our power systems. So things like extreme events and climate change and the demand side. We just heard about that in the last session with some of the DERs and VPPs, and resource adequacy came up a couple of times in that session. Resource adequacy has come up in many of the transmission tracks as well. So really resource adequacy is touching all of these different pieces of the system, and we need a more integrated approach, a more rigorous approach to how we're assessing resource adequacy. So you're going to hear from the speakers today. There's 5 outstanding presenters. We have representation from the US and from Europe, and we're going to hear how they're in their individual organizations and capacities are improving and increasing the robustness of the methods and metrics and data that are being used. So I think this is going to be a great session. And we're going to start with Derek Stenclik, who is the founding partner from Telos Energy. He also is leading the ESIG Resource Adequacy Task Force, which, pro tip, there is a report that just came out from the most recent round of that resource adequacy work, looking at a multi-criteria framework, which is what he's going to talk about today. So hot off the presses, and I'll hand it over to Derek.
Great. Thank you, Bethany. So as Bethany just mentioned, I'm going to be talking about the new report. It just released this past week. It's an ESIG report through the Resource Adequacy Task Force. And really what my conversation is going to talk about is new resource adequacy criteria. So kind of just a little bit of background into the Resource Adequacy Task Force from ESIG. You may have seen some of the previous reports. So this is the 3rd report in a 3-part series. Well, maybe a 4th, we'll see. But the first report was really a 2021 report around redefining resource adequacy for modern power systems. And here we looked at new probabilistic methods, new ways to think about how do we, with a changing resource mix that's reliant on variable renewables and energy limited resources, becoming more weather dependent, how do we make changes to the way we evaluate resource adequacy? So that was really around first principles of resource adequacy and analysis at a system level. The second report, this came out in last year, was really around ensuring new designs for capacity accreditation. So while the first report was looking at system level studies, the second report was looking at how do we measure the capacity contributions or the resource adequacy contributions of individual resources or types of resources. And so the third, really building on that, is what we just released around new criteria. And so what we mean by criteria is what level are we planning to design our system to? How reliable of a system do we want to have? And so North America, most places are using the 1 day in 10-year loss of load expectation, the 1 day in 10, as the reliability criteria or the resource adequacy criteria. And that's driving our minimum capacity needs, it's driving our capacity market requirements, and it's driving planning reserve margin requirements. And so we looked at that and said that's been around for decades. It's been the pivotal planning paradigm for much of the way we make investments, but we had a question, is that keeping up with the resource mix changes, the changes in load, and do we need to think about new criteria and new metrics for that? And so we came up with this task force that had over 40 experts across a wide range. So from utilities, system operators, regulators, reliability coordinators, developers, and researchers. So first, I want to give them all a lot of credit for all of the feedback and buy-in and work they provided. But I also want to highlight, we went into this and I felt pretty daunted, to be honest. This is the 1 day and 10-year planning criteria that's been around for decades, and it's been kind of the staple of the industry. And who am I to walk in and say, no, we need to change that. We need to completely, or in some respects, move away from that. And so that's really what this task force was all about, is pulling together, trying as best as we could with a sample of 40 to get some industry consensus around this. So first, I really wanted to use this slide to set the stage for the rest of the panel, go over some terminology and some of the building blocks of resource adequacy. So the first around adequacy assessments and studies. So this is the way we take probabilistic analyses and we look at, do we have enough resources to serve load across a wide range of uncertainty, from weather uncertainty to load uncertainty to generator outages. And we've seen a lot of improvements into those methods across the industry. The second are resource adequacy metrics. That's how we measure the resource adequacy risk on the system. So these are things like loss of load expectation, loss of load hours, expected unserved energy, and other various metrics. And so those are outputs of those adequacy assessments and studies, and it's the way we actually quantify and measure resource adequacy. The third is capacity accreditation. So again, we take those first two and we use it to actually measure the contributions of individual resources or fleets of resources for the resource adequacy that they provide to the system. So in many places, this is effective load carrying capability, or ELCC, which relies on probabilistic assessment and those metrics. And then lastly is the resource adequacy criteria. And this is the minimum threshold that we are planning to. It's how it answers the question, how reliable of a system do we want, and how much are we willing to pay to have that reliability? And so each of these four things work very closely together. They are all linked, and they all have to be linked in order for any one of them to work. And so I really want to just have this here to set the stage for the rest of the panel. I think Arne's coming up next, and he has a really great presentation that really shows how these different metrics, accreditation, and criteria all work together to plan our system. So again, when we first started this task force, again, I felt daunted going in and trying to say this 1 day and 10-year planning framework that we've been using since the 50s. Do we want a change to that? It's a lofty ambition. And so before we started, we did several surveys. And so the first question was, should the industry consider a new resource adequacy criterion? Should we move past that 1 day and 10? And pretty overwhelmingly, we ran this across 3 different surveys. Nothing scientific about these surveys, but we did, there was an ESIG webinar on probabilistic resource adequacy methods, had 116 people participate in the survey. We had the task force, we got 32 participants, and then we had the IEEE resource adequacy working group with about 30 participants too. An overwhelming 75% of people said, yes, we need to move past the 1 day and 10-year. I was frankly surprised to see that many people on board. And the second one was, if we had to move away from one resource adequacy criterion and we had to pick one, which one would we pick? And here, this is a little bit of an unfair question because we gave a multi-metric as an option. So we gave people a little bit of an out, and that's what most people chose. It said really one metric is insufficient, so we need to kind of have a combined approach or multiple metrics. And really, the fundamentals, we go over this in the report, but the limitations of the current use of LOLE at 1 day and 10, and in Europe, it's a loss of load hours, but a very similar construct around how we measure risk. So right now, in many places, it's a line in the sand, right? We determine a system is either reliable or it's not, whether or not it meets the 1 day and 10-year criterion. In reality, reliability is this continuum, right? And it's all about this trade-off between cost and reliability. And today, again, we're treating in most regions this as a line in the sand. The second is it's inadequate at differentiating between events, right? We're treating all events as if they're equal. A 2-hour event in the summer evening, it's being treated the same as a 12-hour event in an extreme cold period, right? It's not differentiating between size, frequency, duration, or timing of those shortfalls. It's treating them all together. The third, it's a static criteria and used to represent a dynamic system. So the system is always changing, and yet we've held to a single criteria throughout that period. And then lastly, the risk profile itself, where risk is showing up, when it's showing up, why it's showing up. All of that is changing very much as the resource mix evolves, and again, not changing the way we measure that risk or embed it in our criteria. Oh, there we go. So 3 final recommendations from the task force. If you take away nothing from this presentation except this slide, this is it. So the first, and I'll go over each of these. The first is transition to a multi-metric criteria. So today we have a single 1 day in 10 LOLE. The first recommendation was to move to a multi-metric criteria. There are a few places doing this. Northwest Power Conservation Council, NWPCC in the Northwest is doing this. A few utilities in Colorado are doing it. ERCOT is proposing it. So there are some people that are starting to think about implementing this, but again, it was the first recommendation that came out of this task force. The second is, again, linked with the first, is to specifically consider extreme events or tail events, right? And while most of our resource adequacy metrics, whether it's loss of load expectation or it's EUE, expected unserved energy, they're all average indices. They're just measuring across a wide range of potential shortfall events. What's the average of each of those metrics? But in reality, when we think about reliability, resilience, it's really the tail end of those distributions that we're most concerned about, right? They have the most impact on economics, on cost, on human life. And so we want to make sure we're capping how bad things can get. And the third is to incorporate economics and to really show that there is this inherent trade-off between cost and reliability. And we want to make sure that's transparent and that we're deciding what level of reliability we want based on what it costs us. And so I'll go through each of these quickly in my last 5 minutes. So the first, around transition to a multi-metric criteria. Today, loss of load expectation really only represents a single dimension of risk. It measures the frequency we can expect to have shortfalls on our system, but it doesn't tell you anything about the size of the events, the depth of those events, the impact of those events, or the timing. And so you can see from the scatter plot, this is some analysis we did for an ERCOT case study, and it shows on the left the current grid, kind of today's ERCOT system, and it's showing both, and then on the right, a high renewable system. Both of these have the exact same LOLE. They're 1 day in 10 LOLE, but you can see by the dots, which are measuring on the x-axis, the duration of shortfalls, on the y-axis, the maximum size of those shortfalls. So again, the high impact events are in the upper right quadrant. They're long and large. And then the color of the dot is the season, whether it's summer in red and winter in blue. And so you can see everything shifting here as the resource mix and the load changes. We are moving to a winter risk dominated system. And you start to see those events get larger, right? We're moving to an energy limited system. And when we do have shortfalls, they can become larger. And so we want to make sure we capture that changing risk profile. Another thing on the multi-metric criteria is unexpected unserved energy is a preferred addition. So we need to make sure if we're moving to an energy limited system, we should have a metric that tracks unserved energy, right? It makes sense. We're moving to the system based on variable renewables and energy storage. We want to make sure we're tracking unserved energy implicitly. And so this is just an example as you move to a system that has a lot of storage as the primary source for reliability, the way you dispatch that storage, you can make your resource adequacy metrics do whatever you want. You can try to make them shorter, you can make them less frequent, but what stays the same across every case in an energy limited system is expected unserved energy. So it's a more stable metric especially when we look out at an energy limited system. And then I've talked about this quite a bit, but again, no one metric is the solution. So this is coming out of some preliminary work from PJM, and it just shows, again, for one system, that's a 0.1 LOLE. Well, when do those loss of load events occur, and how do you measure it? If you're just using loss of load expectation, it looks like most of our events are in the summer, and so it's going to be driven by that summer risk. If you look at it from expected unserved energy, though, the events that occur in the winter, while they may be less frequent, when they do happen, they're much more impactful. They're much larger. So that second recommendation, specifically consider extreme events. So, I've said this already, but not all resource adequacy loss of load events are the same. And the tail risk can have a disproportionate impact on reliability, cost, and human life. And so we want to make sure we're not just managing the average or expected resource adequacy criterion, which we do with loss of load expectation. We also want to look at that tail. How bad are the worst case options? And so this is one option. There's other ways to do this, but basically the value at risk metric and the conditional value at risk metrics, they both look at whether you're looking at size, duration in megawatt hours or maximum shortfall in megawatts. It's basically saying let's look at my full distribution of outcomes in the resource adequacy study, where we might have hundreds or thousands samples to choose from. And let's look at the tail end of that distribution and let's cap it. So we could say, I want to make sure that 97% of all of my shortfalls are 8 hours or less, right? And we want to make sure we're capping something at how bad that worst case can get. And this is a good dovetail on for those who were part of the resilience session in the previous panel around a need to specifically in those extreme events move beyond just this probabilistic approach. We're quickly moving to a system that is more weather dependent, and it's not just this random occurrence of different things happening at the same time, forced outages happening randomly when we happen to have high load. But it's really when a specific weather event comes in, it's going to stress the system. It's not a matter of if that will happen, it's just a matter of when. And we don't necessarily need to assign a probability to embed that in our planning and our resource adequacy criteria, but we can make sure that the system is robust against that stress testing event. And then lastly, incorporate economics. This one seems obvious, right? But it's not being used in practice today. So really, reliability and cost are an inherent trade-off. If you want a more reliable system, you'll have to pay for it. If you want to have savings, you'll have to live with a less reliable system. And so making sure you're balancing that trade-off correctly is critical, especially when we think about the investment decisions we're making and the size of those investment decisions. And so having a way that transparently shows this trade-off, as opposed to just saying, we must get to this level of resource adequacy. There may be times where it's relatively cheap to move beyond that, and we can get more reliability for relatively cheap. There's other times where we might be willing to live with a little bit less reliability because it's not worth the cost to get it. So again, just making sure that's transparent. And so hopefully that does a good job setting up for the rest of the panel. I'm really excited to see what others have to say. And again, please go check out the full report.
Awesome. Thank you, Derek. Yeah, so I think those three key takeaways are really important to keep in mind. So the multi-metric or multi-criteria framework, specifically considering stressful events and incorporating economics. So next up is Arne Olson, who is a senior partner from Energy and Environmental Economics, or also known as E3. So he's going to be taking us on a journey looking at a specific system, and as Derek mentioned already, looking at a couple of different planning reserve margin methods. So Arne, take it away.
Thank you. Okay, I'm taking us on a journey from this beautiful place, Tucson, to another beautiful place, Hawaii. I'm going to talk about some work that we did for Hawaiian Electric under direction from the commission to look at different methods of assuring resource adequacy in their long-term planning. I'm going to just give you a brief introduction to the project itself, take a step back and talk big picture about the methods that we use to measure resource adequacy and to accredit resources toward the resource adequacy needs. talk about the testing that we did of 3 different methods for evaluating resource adequacy using Oahu as a test bed, and then go into what the results of our test are. So just a quick introduction, this study ended up encompassing all of the islands that Hawaiian Electric serves, which is all of them except for Kauai. But we used Oahu as sort of a test bed for this comparison side by side of 3 different methods of evaluating resource adequacy. Hawaii, like many other jurisdictions, is undergoing significant changes in the composition of its electric resource portfolio. The stack on the left is kind of more or less what they have today. A lot of energy coming from thermal, increasing amounts coming from wind and solar as well. But they're trying to move to the one on the right, which is just about all solar, a bit of wind, maybe some offshore wind, a teeny tiny bit of dispatchable there at the bottom. And so very, very large changes. And so they need a resource adequacy framework that's robust across time and across all of these different changes. So really my talk is about how to do resource adequacy constrained capacity planning. So we're basically taking these resource adequacy metrics and measurement methods and incorporating them into long-term capacity expansion modeling and using them to help inform our future portfolio construction. And the 3 methods that we looked at, and I'll go into these in more detail, are ERM, energy resource margin, which is the method that they use today, plus HDC, which is hourly dependable capacity. That's what they use today in Hawaii. It's a homegrown method. There's another variation of that, that's energy reserve margin plus hourly expected capacity, which I'll talk about. And the third one, which is more of a standard PRM ELCC method, and that's actually the one that they were instructed by their commission to evaluate. And I want to take a moment here and give a huge shout out and thanks to the technical advisory panel that assisted us on this project. Derek Stenclik, where did he go? Was a member of that. Elaine Hale, I saw her as well. And a couple of other names that you'll recognize, Aiden Tui, Matthias Fripp. So we really, really appreciate all of their inputs. And I want to also mention Adrian Au is with me here from E3 as well. Where are you, Adrian? Right there, and he can answer all the hard questions that I can't answer after the talk. What we see today in Hawaii, like many places, is that reliability events tend to occur when due to a combination of high loads and larger than expected amounts of thermal resource outages, right? Stuff breaks, it's hot, they can't quite meet all their load. This happened just a couple of months ago in Hawaii. That's what we expect. They're moving to a world where the biggest reliability events are going to be different. They're going to be large energy shortages that occur typically in winter. Even in Hawaii, there are seasonal differences in the amount of solar production, and there may be long periods of cloudiness, and they might run out of energy. And that's what you're seeing on this graph. I know there's some concern among various analysts that the standard loss of load ELCC methods might not be able to be robust enough to address this type of concern in addition to the one that we saw on the previous slide. And so that's what we're going to talk about a little bit in this presentation. So just taking a step back on how we traditionally consider resource adequacy, we typically will do something like calculate a resource need. We'll do that by running a loss of load model, and we'll add capacity until we meet our standard, whatever that standard is. Usually it's 1 day in 10 years, as Derek said, 0.1 LOLE, but it doesn't have to be. It can be LOLH, it can be EUE, it can be a number of different standards, but you have to have a standard. You add capacity until you meet that standard. The amount of capacity that you add, that's your total need. And then the reserve margin is the residual calculation from that, where you divide the total by your 1 and 2 peak load, subtract 1, and that's your percentage reserve margin. It's a residual calculation. It's not a thing by itself. That's something that people often lose sight of, but it's useful just to help you understand how much extra I need across a broad variety of scenarios. Now, this ignores a whole bunch of things that are changing. Our world's getting more complicated. I think it's well understood by now that there are interactive effects among resource types, including cannibalization and diminishing marginal returns. As you add more solar, you push the peak into the evening, the next tranche is less effective. As you add more battery storage, the next resource adequacy problem becomes more elongated, and you have to add more hours to continue to have the same effectiveness. So that's well understood. It's also, I think, by now well understood that when you add solar and storage together, the whole is greater than the sum of the parts. They complement each other, and so you get more out of them. That's just an example of the type of interactive effects that we now have to consider when we calculate our resource need and when we do our resource accreditation. Another way of thinking about this is that the way that we've done resource accreditation in the past is kind of nice and simple and linear. We could do it this way because we had small differences in performance among different resource types during the times that matter, and largely no interactions between resources, or at least ones that we couldn't ignore. And we could do performance penalties to incorporate forced outages. So you could pretty much just add up the nameplate of all the resources, add some extra, for the extra margin in case those resources weren't available when you needed them. And then you built to that standard. And so your installed capacity was just kind of the sum of your nameplate capacity. Nice and simple. But it turns out we were living, we didn't know it, but we were living in a linear simplification of actually a much more complex problem. What we have now are large differences in availability during the key hours, significant interactions among different resource types. And so our portfolio ELCC, the combined capacity contribution of all the resources, is no longer a simple linear sum of the individual resources. It's now a complex function. And we need to change the way that we think about doing resource need, measuring it, and doing resource accreditation. So it's not just the sum of all the nameplates, socializing the forced outages. We now have to look at each resource on its own and consider how it performs during the most important events. Another way of thinking about this is that the portfolio ELCC is a complex function, as I said, of all the resources that make up the portfolio. It has this convex shape that as you add more megawatts, the effective capacity that you get from all of them tends to diminish. The height of the surface is the total amount of effective capacity from the portfolio. But what we're actually interested in with respect to resources is how much each one helps us meet our total need. So if I make a small change in the total portfolio of one type of resource, then I measure how much that helps me avoid a capacity to meet that capacity need. That in effect is a partial derivative of this multidimensional surface with respect to that one resources dimension. So that's the marginal ELCC, and that's the quantity that we're interested in and need to look at when we're thinking about making changes to the portfolio. How much does this marginal change help me meet my total need, whether that's a retirement or an addition of a particular type of resource? So we think of the total need as a surface, a multidimensional surface that's made up of all the different types of resources that are part of the portfolio. And we'll come back to this surface in a little bit. So just keep that kind of image in mind. So with that background, now what did we do to test the different resource adequacy methods on Oahu? So just to give you a little bit more detail about how they do it now. Again, I mentioned the hourly energy reserve margin and the hourly dependable capacity, HDC method. So this is a homegrown method that they came up with. They, in effect, make sure to plan their system so that they can have a 10% margin in every hour. And the way that they arrived at this is they, in effect, take a load shape and they match to that load shape on an hourly basis the 1 in 5 production of solar and with the 1 in 5 production of wind. So for example, you're looking at on the bottom, June 4th. And so if it's June 4th, they'll take on June 4th at noon, they'll take the 5 latest years of solar production, June 4th at noon, and they'll take the lowest amount, the 20th percentile, the most conservative of those, and they'll say, that's what I can expect from solar on this day. And similarly for wind, during that same hour over the past 5 years. So it's an exceedance type of a method. So, it's a simple method. It's a conservative method. It's workable, but it has some drawbacks. One of which is right away you can see that you're losing any load and wind and solar correlation. Is you're looking at load solar across different years, matching that with load across different years without having a weather match. So the technical advisory panel and HECO came up with a potential improvement on that, which is to do an expected capacity on an hourly basis rather than an exceedance-based method. And so this is where instead of just taking the worst of the last 5 years, you actually line up all 5 years, load, wind, and solar, weather matched, and you implement that as a constraint in the capacity expansion model, sort of brute force. I'm going to make sure I have enough energy to meet all my loads across all of those 5 years times 8,760 hours. So 40,000 separate constraints to make sure that I have enough. And I'm going to make sure that I serve load across all of those hours. And so that rectifies the problem that we saw of making sure that you have a weather normalized or weather appropriate load, wind, and solar shapes. And then the last one is the planning reserve margin plus effective load carrying capability method that I talked about. So this is where we define, it's a separate reserve margin constraint and a separate resource accreditation constraint. And the constraint says that you have to have enough capacity so that the accredited capacity to meet that load plus the reserve margin, with the reserve margin having been calibrated with a loss of load study. So we call this an ELCC for all approach. We use ELCC to accredit not just the wind and the solar and the battery storage, but also all of the thermal resources. And on smaller systems, especially systems that have constrained maintenance hours, like a tropical system does, where there's not a strong seasonal pattern in the weather, the ELCC value of a thermal resource can be significantly below its nameplate. So this is a real issue on how to accredit thermal resources on this type of a system. ELCC, in our experience, accounts for really all of the factors that can limit the availability of a resource: variability in output duration, seasonal temperature derates, forced outages, energy availability, fuel availability. Really, all of that goes into the model and affects how the resources are performed during your simulation. And it does consider extreme conditions, as Derek talked about, being very important. Back to the surface. So the way that we actually incorporate different levels of wind and solar and battery storage across all the potential different futures between now and 2050 is to take that surface that I talked about before and try to measure different parts of it, the parts that are important for their portfolio construction. And the way that we do that is, in effect, measuring marginal ELCCs at different points along that curve, different saturation levels, and of different combinations of wind and solar battery storage. We can use those different measurements to make a linear approximation to that convex shape. That's what you see on the right. And then we incorporate that into the capacity expansion model as a series of different linear constraints that say, as I go up that curve, up that saturation curve, then I piecewise linearly reduce the amount of capacity that I can expect from that type of a resource. And you can do this in multiple dimensions by measuring different combinations of wind, solar, battery storage. In this case, we use a two-dimensional surface that incorporated both the capacity of solar and the capacity of storage. We've also experimented with three-dimensional surfaces where we also incorporate the duration of storage as well. So this, again, is all just meant to constrain the solution that the long-term capacity expansion model arrives at, to help ensure that it will produce a resource adequate portfolio. And we hope that it's robust across this wide range of potential futures. So the way that we then evaluated the different methods against each other was we ran them through the capacity expansion model. That's our resolve model, which we use in Hawaii. And then we tested the outcome in our recap model, which is a loss of load model, to see, did the capacity expansion produce a reliable portfolio or not? Or what do we have to do to make it produce a reliable portfolio? So to get in to the results quickly, what we found, punchline, at a high level, you could make all of the models produce a reliable portfolio. And they all came to that same a similar portfolio at a relatively similar cost. So the left just shows the different colors are different resources in the portfolio. The green is firm, the yellow is solar, the purple is storage. It's more or less the same portfolio across all of them. We made them all meet your same 0.1 day loss of load expectation, but there are some differences. And in particular, the differences are on the number of iterations that we had to go through back here, this washing machine between resolve and recap, to make the portfolio become reliable. The HDC method, the one that HECO uses today, just one run, 10%, bam, hit the target. You know, I don't know if they were lucky or good. I think they probably are good because, you know, our brains are really good learners. And I think there's a lot of experience that went into that. And so I think that actually is something that they are comfortable with, they've used, and it worked in this case. We're not sure how robust it is against, you know, different futures, but it worked in this case. The HEC method, which we all agreed was an improvement on the HDC method, was much more difficult. We had to do 8 iterations back and forth to get it to a 0.1 day standard. And we had to use a minus 2% reserve margin to get it to meet our loss of load standard, which we had to scratch our heads about and think about what that really means. And I think we finally realized that what that means is that in those 5 years, was a pretty extreme set of weather events. And so serving all load within those 5 years is more reliable than a 1 day in 10-year standard. So there's probably one of those days that you might not need to serve with 1 day in 10 years is the standard. And that is what we were measuring it against in this case. So that was a little bit funky in that case. And our ELCC method with 2 iterations, we had to make one adjustment at the end to get there. It did have slightly lower cost and slightly less unserved energy than the other methods. So, they were kind of really a tie with respect to the portfolio construction. So that really made our qualitative evaluation of the different methods very, very important. And here we looked to the work that Derek and others had done at ESIG on what other metrics we should be thinking about, what other characteristics our systems should have. They should be non-discriminatory, they should be transparent, they should be predictable, they should be reliable. We added a couple, we should have less complexity if possible, they should be least cost. And so we evaluated the different methods using these different criteria. So this is E3's scoring of the different methods across the different, the 5 different criteria: robustness, non-discriminatory, transparent, et cetera. With respect to robustness, we thought that the ELCC method was clearly superior because we have a reserve margin that's dependent on load only, and you're giving each resource a haircut based on its ability to perform across all the variety of different conditions. Whereas under the ERM methods, the reserve margin was dependent on the portfolio. So not only was the performance moving, your target was actually moving as well. But the ELCC method is also non-discriminatory. It's ELCC for all. The thermal resources were accredited using the same method as the renewable resources. Whereas under the energy reserve margin methods, the thermal was just given basically a nameplate capacity, and it was mostly focused on the performance of the renewables. None of them was transparent. These are black box models. Let's just be honest about that. They're all complex as well. And none of them are very predictable unless you had a lot of experience working with them. We gave the ELCC method a high mark on predictability because we have a lot of experience working with them. We understand how they work. We kind of have a sense of how things are going to turn out. And we think others will as well as the industry gains experience with these methods. So our clear preference was for the PRM plus ELCC method, and that's what we recommend that Hawaiian Electric move forward with. I will say the TAP, we asked the TAP to rate these methods using a similar scale. Their ratings weren't the same as ours. I think I'll summarize their feedback as saying everyone preferred the one in the middle, the hourly expected capacity, versus the one that HECO uses now, which is the hourly dependable capacity. But there wasn't a strong preference between the HEC and the PRM and ELCC methods. So I think with that, I'm over my time and I'll sit down and wait for the next one. So thank you.
Thanks, Arne. So while we're transitioning here, I guess a little commentary. So hopefully it's clear to everyone that there's the system target. So Derek talked about that, how there's this need to reconsider how we're establishing what that target should be. You're having multiple targets. There's how you accredit individual resources that contribute to meeting that target. So the ELCC fits in with that. Out of the second report from the task force that Derek mentioned at the very beginning. And then there's how do we fit all this together with our capacity expansion models, kind of the broader investment procurement processes. And so Arne touched on that a little bit with the washing machine slide. And so I know there's a number of folks in this room who are also thinking about that in their individual organizations. So lots of work happening on all the pieces that fit into this broader resource adequacy landscape. So just in case that helped to connect some dots, but I think the slides are ready, and we'll move now to the middle of the US, so to MISO, the Mid-Continent Independent System Operator. So we have Durgesh Manjure, who's a Senior Director on Resource Adequacy Planning at MISO. And he's going to talk about their improved probabilistic methods within the ISO.
Thank you. Can you hear me? Okay. I think I'm going to stand up for old man LOLE. Looks like a lot of LOLE bashing that we just heard. But it's not without value. So we'll go on a little bit of a journey, what MISO's been doing over the last several years. We are not different in terms of the issues that we're seeing compared to other grid operators, but some of the progress that we've been able to make does involve a lot of probabilistic modeling, and we do rely upon the LOLE model as defined historically. But certainly we are open to change, and we'll look at some of the things that are in various different stages of development across MISO. So this is a standard commercial for MISO. They make us do it, otherwise kind of we adversely impact our bonus. You might have seen it in other MISO presentations as well. What may not be apparent from kind of this commercial slide is MISO's footprint spans 15 different states. And at the heart of it, resource adequacy is a load serving entity obligation and the states that oversee it. So where the challenge kind of gets most accentuated when it comes to policy making across MISO is how do we balance the needs and aspirations of 15 different states, going from all the way to North Dakota to Michigan on the east and then Louisiana in the south. So we'll touch on that a little bit in terms of how we navigate the stakeholder process there. But also some of these values that you're seeing in terms of benefits, a lot of that is kind of capacity avoidance that occurs in the footprint. And frankly, all of that analysis currently relies on our existing methods that rely on the LOLE criterion. So certainly there is a need for change. There is lots of drivers, and then we'll look at some trade-offs that we are currently looking at to see where should we be going. But we'll start with what's happening to MISO. As I said, not unlike any other operators or other countries in the world as well. Two main drivers to why we should be evolving and changing how we run the system. So at the most fundamental level, MISO essentially is trying to make sure that we both run and plan a reliable and efficient transmission system. And we do that through different markets. I mean, we have a capacity market. Well, it's an auction. We have the FDR markets. We have day-ahead and real-time energy markets. However, that operating paradigm is changing significantly. As you can see on the top right, once in a 100-year event, it's probably occurring every 2 to 3 years. And while that's a fertile learning ground for how we should be kind of operating the system going forward, the other transitioning or the other kind of main driver for why things are changing is on the bottom left there with the fleet evolution. So I apologize for the small chart, but I was trying to get to the story in one slide. So what you see on the bottom left is all the retirements on the extreme left and the new generation that has historically been built. So all the green and then a little bit of orange or yellow, that's the solar, but the green is the wind. And then all the black and the blue kind of pointing downwards, those are all the retirements of coal and gas. So very obviously we are losing coal and gas capacity, and that is being replaced by solar and wind. So I'll not get into the accreditation details of those, but for those of us who are familiar with what that means from a capacity standpoint, we are losing lots and lots of capacity very quickly. And as a result, before that, and what you see on the right side is those four, it's what's in our queue. And this is actually a snapshot from 2022. So the queue has grown since then. But as you can see, there's no black or lots of blue in the queue. So it's all solar and batteries and hybrids and co-located storage and so on and so forth. So going forward, there's no doubt our fleet is going to change. And it has already started to impact the emergency situations we see on the system. So before 2016, what we would like to call the good old days, that's kind of the bottom right chart with no skyscrapers. We didn't have any summer or non-summer emergencies. But as you start to progress towards the right since 2016 onwards, we've had a consistent set of emergency declarations. And most interestingly, they're not limited to summer. In fact, in some years, we had more emergency situations outside of summer than during summer. So even though as our operations paradigm and then the associated risk is evolving, bringing it back home to resource adequacy, we still rely on the traditional criterion, right? All of our studies currently use the loss of load expectation study and the criteria of 0.1 in 10 or 1 day in 10 years. So I'm not going to elaborate that, we already heard that from Derek and Arne. I mean, it's a frequency of loss of load. It doesn't cover kind of how deep is the issue in terms of load loss. It doesn't cover the breadth of the issue in terms of how long the loss of load was. So there's certainly several limitations or limited insights that you can gain from that criteria. But it does underpin all of the key components of resource adequacy. So it's not without use, and very simplistically, right? I mean, if you put all the simple problems in the world in one box, resource adequacy would be outside. But trying to kind of really simplify that down, what you need is how many megawatts do you need to maintain reliability? That's our requirement. And then how do you count the megawatts that you have? That's your accreditation. And then what's the price at which capacity would be available? That's your pricing. So we have different, PJM does the actual capacity market. We have an auction, and different people do it differently. So coming back to requirements, I mean, we have a planning reserve margin requirement across the footprint. And then I didn't mention the zones, but our footprint for resource adequacy purposes is divided into 10 different local resource zones. So we have a requirement for each of those as well. And both of those studies or both of those requirements come out of a study that uses our LOLE one-day intent criterion. Accreditation, it's evolving. I will talk a little bit more about that. We've kind of started to use historical risk periods. So I feel good when I read the ESIG report. We're starting to check a lot of boxes that actually ESIG is recommending. So we're already doing a lot of that. So we'll talk a little bit. And then going forward, we are going to look at availability during projected risk hours. And that's our revised accreditation that's expected to be filed actually this week as well. But both of those rely on ELCC type studies historically. And then going forward, we'll have a LOLE study, again, using the 0.1 criterion. And lastly, it's in terms of pricing. So today we use a vertical demand curve that uses the planning reserve margin requirement or a PRM based on the one-day intent criteria. Going forward, we have a filing active at FERC. We are hopefully going to hear back from FERC soon, where we would then deploy a slope demand curve, which will again be based on varying levels of PRM around the 0.1 criterion as well. So some of these are future, not all of them are implemented, and we'll see kind of the progression or the continuum of reforms that are happening at MISO. Extreme left of your side, again, as those are the good old days. We're fat and happy, lots of reserves, lots of coal capacity, never had any issue. So we were content with just looking at the summer as a proxy for the whole year. We would make sure that we have enough capacity to handle like July 15th or August 15th, 2 p.m. in the afternoon, and we are good for the rest of the year. And that actually truly did work out for the most part. But then we saw those skyscrapers, all those emergencies that started to happen outside of summer. So that was a big impetus for our seasonal construct, so which was implemented last year. It was a very, very fast implementation. I guess we filed in 2021, FERC approved in 2022 September, and we actually implemented already in April of 2023. So it was a fast implementation, but it did give a lot of benefit. And I won't be able to cover all of them, but for one, we now have seasonal requirements. And both of the winter events that I talked about earlier, Uri and Elliott, they were both winter events. So historically, we would have like a 7 or 8% PRM that's calculated from summer for winter as well. But if you look at the winter requirements, they are a lot higher because of those events that are now factored into our modeling. And likewise for fall and spring, which are heavy outage seasons, and that translates into higher requirement for those seasons as well. The third block from left, along with the seasonal construct, we also had a change to our accreditation methodology. This is the first time we are trying to tie in, if you will, the planning piece and the operating piece. So a resource is granted accreditation based on how well they performed when MISO needed it to perform. So this is when we had times of need or times of, we're calling them critical hours, where you're either short or within 3% of the margin. During those times, how did the resource perform? And that is what is used to accredit the resource. So that has changed significantly the behaviors from our members, from our asset owners. So in terms of outage scheduling, so we are seeing people being very mindful about how they schedule their outages because they want to avoid adverse impacts on their accreditation. So it is paying dividends already. This is only second year. Actually, this week is when the auction is going on. So I'm kind of distracted a little bit. The auction window just opened yesterday. It's going to close on Friday. So lots of things happening at MISO. But we are very happy with the seasonal accreditation as well as the construct because it really gives us insights that we didn't have before across the 4 different seasons. And they are very different. Both the requirements as well as the accredited value of our fleet is very different. Going further, one more step up is the reliability based or slope demand curve I talked about earlier. So that is not implemented yet, but we are working hard to implement it for the next year's auction. It's still active at FERC, but as I said, instead of using a vertical demand curve based on a PRM of 0.1, we're going to use a slope so that prices don't become binary. What happens right now is if you're surplus, prices go really low. Like last year, we had $2 per megawatt day. But you're deficient, then prices go all the way to cost of new entry, like we had in 2022. So there is no kind of granularity in cost or the price of capacity. So that's what we're trying to achieve through the RBDC. And finally, it's the accreditation. So this is where I said we check almost all of the boxes from the ESIG report. Kind of it's based, we have one common methodology for all resources. It is based on risk hours, not just peak demand. It is based on operational performance, not just a planning model. And I think 2 or 3 that I'm forgetting, Derek, but you can help me going forward. So I'm not intending for all of us to read this, but what it's trying to show is with each progressive reform, our dependence and the need for elaboration of the LOLE model is increasing. We are more and more heavily relying on the LOLE model. So annual construct, we just had the PRMR or local reliability requirement based on that, and then we used to only do the wind ELCC studies. With the seasonal construct, we're doing it for each season. We're kind of 4 times, if not more. With the RBDC, all of the marginal reliability improvement curves and the RBDC actually will be computed using the LOLE model. And then, of course, the accreditation, we're going to put the whole fleet into the probabilistic model. So earlier, it was just the thermal piece of our fleet, but now it's going to be thermal, wind, and everything. And actually, the requirements will come out of that same model as well. So we are basically putting all our eggs in that one basket. So we want to make sure that that basket is really strong and robust. And to that end, along with evolving the resource adequacy construct, we are also working on improving our LOLE model. And if you were there in the previous session, one of our engineers, Megan, she's here, she talked about it, a little bit more details about what we are doing, specifically the cold weather outage adders, and then the transmission modeling. So there are several other aspects to the model that need to be looked at. Planned outages is one that we've already started to incorporate and kind of improving it as we go. Seasonal outages, I already talked about that. Transmission is a big deal, but that's a longer term focus. But the correlation of the different outages during extreme events, and Nick asked a difficult question to the last panel. I hope he doesn't ask the same question here. But that's something that we are looking at. How do planned outages actually kind of get distributed between the different resource classes, as well as between times of need versus times of, I guess, surplus, if you will, because it being a probabilistic model, sometimes it might be counterintuitive with respect to what you expect the model to do. So that's something that we are looking at to make sure we don't inadvertently kind of prefer one type of resource class over others. And then reliance on external systems, that's a big one, because if you're in an emergency, and like if you looked at Uri, the whole Midwest or beyond MISO's footprint, everybody was in an emergency. So if you're relying on external support, but then everybody is grasping at straws, how do you count on that support during times of need? So we are going to look at what happens if MISO is going solo, and then what would the requirements look like to that effect. So with the evolving model, though, we've not done anything to the criterion. And certainly we've heard a lot of drivers for the criterion to be changed, and we agree. What you see on the left side of the slide is results from one of the studies that was done. So on the y-axis, you're seeing increasing penetration of renewables, and then kind of the contour map is the levels of expected unserved energy and loss of load hours. So for the same LOLE criteria, so all 3 of them are using an LOLE of 0.1, but you can see the EUE and LOLH is quite different based on the penetration of renewables. So certainly, as I said, there's areas drivers for changing the criteria and making it better. But then if you look at the trade-off, there's so many dependencies downstream, right? On the left there, you see the criterion and the actual risk model, but then all of the existing construct is based on that. All of the reforms that we filed are based on that. Some of the transition timelines are 3 to 5 years. So for the next 3 to 5 years, we have hinged something on this criterion. And then it's not just us. We talked about long-range transmission planning tranche 2 or LRTP tranche 2. So some of the benefit calculations are also based on that. And our members use what we come out with in terms of resource adequacy for their integrated resource plans as well. So there's lots of considerations before we can move on. And then certainly we have many questions and many potential answers, but to kind of tie to back to some of both Derek's and Arne's presentation, like how do we convince ourselves that changing the criteria, even though everything says you should change, how do we convince ourselves that it is going to be better? And what does better mean? So clearly we're in the space of more questions than answers at this time. So currently our answer is it depends. And we are going to work on this in the next several years before we are able to actually pull the clock. So with that, I think that's my last slide. Yep. Thank you all.
Thanks, Durgesh. Really exciting to see some of the ESIG task force recommendations getting put into practice. So thanks for sharing that with us today. And we'll look forward to hearing the next round of updates. So our next speaker is Anaisha Jaykumar, who is a reliability engineer from SERC Reliability Corporation. So we're staying stateside for the speaker. Where we're switching slides. And so this is our last US-based presentation before we head over to Europe and hear about their more coordinated approach. So that's a pan-European approach. So Anaisha, I think we're ready. Also, it's really raining outside, if you didn't know. Hopefully everyone is staying awake. So if you're struggling with energy, just go walk outside for a second and come back. That'll refresh you.
Let me do a mic test. Can you hear me okay? Good afternoon, everyone. I'm Anaisha Jaykumar. For those of you who may not be familiar, SERC is one of 6 regional entities under the North American Electric Reliability Corporation, and we're in the Southeast. A couple of years ago, we started our journey of doing probabilistic-based resource adequacy assessments in-house. So for today, I'd like to focus on our model, some of the takeaways, but more broadly focus on some key concepts that may not always be obvious in probabilistic-based modeling. And hopefully that also adds some context on how should we be applying our results, knowing that they can be very statistical. So just some practical pointers on what can we take away from them. I'll also be talking about our extreme winter modeling, which was very insightful, particularly for a wide region that has a lot of diverse geographic climates. So SERC is a nonprofit, and our mission is to essentially reduce risk to the reliability and security of the bulk power system. Just to give you some context of the system size, as of 2024, capacity resources is about 310 gigawatts, close to about 260 gigawatts of total internal demand, and about 122,000 of transmission miles greater than 100 kV. SERC is kind of unique in that we have a volunteer-based stakeholder technical committee structure. So the resource adequacy model that I talk about was created with a lot of active participation from our stakeholders like Duke Energy, MISO, TVA, FRCC, Southern Company. They were very involved in what data goes in, the kind of assumptions that we make. And these results are, of course, published publicly on our website. but they are also part of the NERC assessments, like the long-term reliability assessment. And SERC also does state outreach. So we take our assessments and then we communicate the results to regulators, policymakers. So there is a section of my presentation focused on communication of these because, like I said, some of it is very statistical nature. And for a non-technical audience, I can't emphasize enough on how we want to communicate these results and what we want to take away from it. So probabilistic tools allow factoring multiple variables. I have a handful here to give you an example of what SERC does. So in our model, we studied 2 years, year 2024 and 2026. And for each of them, we did an 8760 hourly assessment. We used 40 years of historical weather-based data set, which was used to not only scale load, but also our resources, particularly solar. We used NERC GADS for generator forced outages. So while we maintain a certain percentage of outage by fuel type, the probabilistic model allows us to randomly find different generators that will be on outage in each simulation. There is some assumptions of planned maintenance schedules. We also factor in load forecast error based on some economic variation. So we use 5 points. And of course, power flow limits between our regions. So just to give you an example, a simulation count could very easily be 5,000 simulations each hour of a steady year. So just to keep in mind that the complexity of a probabilistic model can very easily scale. So we want to be mindful of some practical assumptions we can do and make the model more realistic. Something I failed to mention here is, so for the SERC region, for the sake of planning, we choose a multiple assessment areas. So I have here like SERC Central, Southeast, East, Florida, parts of MISO, and PJM. And for our model, we do have power flow limits between them. So although our stakeholders might have their individual resource adequacy models, they definitely see the benefit of a region-wide planning model. And like was mentioned in another session, there's a benefit of seeing what's beyond our own system. So some assumptions that may not be applicable are sometimes captured very well in a region-wide model. Here are some data requirements that we used. And I added a slide here mainly to point out that when we look at our results or results from different regions, we want to be mindful of what data and what assumptions are being used because they can have a very big impact on the results. And so to give you some context, I put some examples here. So for load capacity forecast, our SERC registered entities provide data directly to us. So we have access to that. For solar nameplate, we realized that it's important to supplement it with EIA 860 because there were some gaps, particularly for solar systems less than 75 MVA connected to our systems. So we were seeing a lot of benefit in supplementing our data set with the EIA. Like I talked about, we used NERC GADS, definitely transfer limits, and some assumptions that go into a load forecast error software. Ours is a production cost model, so we do make some assumptions on economic dispatch. And that's also an important piece that other models may or may not do. It may not always be obvious also how historical data is used to project future load. And so I have an example here on the right where we use seed profiles from 40 years, but we also scale them based on our future forecasts. So we're not exactly using our historic data, but there is some scaling going on over there. And there was a really interesting takeaway that I had from the resilience session, and it's making me wonder if maybe we should be using a shorter, more recent data set to capture impacts of climate change and some of the variability that we're seeing more recently that perhaps was not there before. So here on the right, I have a snapshot of some of our results. So we have expected unserved energy on the y-axis, and then loss of load hours on the x. And like was talked about in the previous presentations, I think Derek talked about the importance of multiple metrics. Here's just a practical way of looking at it visually at a glance. So it's very easy to see where kind of different subregions lie, and it can be used in scale in different ways. But for our results, we saw the SERC East region was showing some of the higher risk compared to the others. And I also want to point out that, so let's say SERC East 2026, it was showing maybe around 90 megawatt hours of expected unserved energy. It's important to also give context of what that means to the system size. So normalizing metrics is a really good way to do that. And I have an example here. So when you think about it in terms of net energy for load, it's only about 0.4 parts per million. And I think sometimes that may get lost when we're looking just at metrics without context of the system size or what that might mean, if that truly is a risk or just a factor of the model. Not all events are the same risk. And so, like I said, it's important to use multiple metrics. And in this particular chart, you can see not just the magnitude, but the duration of events. And also it could tell you the frequency of them occurring. Here's another visual for storytelling, and particularly we found this very effective in communicating to our stakeholders. This is a heat map of expected unserved energy. Across, you will see 12 months of a year, and on the y-axis, we have hours of day. So we've used probability-weighted averages to kind of highlight where should we be looking for risk hours. And like I said, with 5,000 simulations per hour, it can be easy to get lost in different scenarios and what that might mean. But here's a good place to start off and say, okay, just high level, where should we be looking before we jump into the details? So for our SERC region, we noticed that winter morning hours were particularly of interest. And a trend that we've been noticing is while some subregions in the SERC footprint are still summer peaking, SERC as a whole has started to transition towards a winter peaking system, and we're in the middle of that transition. So right now we're seeing areas that have dual peaking systems. Statistical results can sometimes be non-intuitive to the audience. And I want to point out an example here that's very simplistic, but kind of tells a story. So if you consider a simple coin toss experiment where if it's heads, you win $10, but if it's tails, you lose $5. The expected calculation would be $2.50. And if I give you just that number, it's hard to know what those extremes are and what range of scenarios it can be. So I give this to point out that when you look at metrics, they might be statistically correct, but they don't always tell you what's going on in the system and the range of possible outcomes. So like was talked about, it's important to do some stress scenarios to see what those kind of end limits might be. And I think what we can really take away is, given there are so many variations and variables and modeling assumptions, we want to focus on the patterns that we see in the narrative and not be too caught up in the numbers themselves. So as promised, I want to talk about our extreme winter modeling scenario. And given SERC has areas with different geography, like I pointed out, we gave a lot of thought to how exactly we want to model a future scenario. One thing that we we're very clear on is we want to avoid any arbitrary scenario model, which may or may not happen. So we wanted to have some science behind how we pick out that future scenario. And we chose, there were the two possible considerations is using our historic data set, knowing that we'll never have perfectly future data. We chose to increase the probability of occurrence of certain extreme winter years. Another alternative that we explored but didn't go with was either keeping the probability of occurrence the same and increasing the intensity of them. Here's an example on the top where in our base case of 40 years, we assumed every year was equally likely to occur. But in our extreme winter scenario, we increased the likelihood of occurrence for certain winter years. And I want to note is that we did do this on a sub-region by sub-region basis, knowing that the historic winter years of Florida, for example, were not the same as Tennessee or some other region. So that at least gave each sub-region their own likely winter scenario, but at the same time, we were able to practically implement it in a model. So we did that such that each sub-region on its own was at a, on a probability weighted average case, it's 90-10. So there were definitely simulations where they did go above or lower, but on a weighted average case, they were at their 90-10. And we also assumed some correlated generator outages. After discussion with our members, we chose to go as 2 times out of the base case, which they which made sense according to their systems. So we did do a step-by-step cases, and I have the base case results here. It may have got cut out, but we're looking at expected unserved energy in megawatt hours. And we did each steps where first we looked at just reweighting weather, keeping our outages the same as the base case. And then we looked at just the multiplicative effect of outages, keeping the weather same. And in our final result, we did combine both. So one takeaway was adding the correlated outages had an exponential impact. So the expected unserved energy wasn't just the addition of the 2 factors, but an exponential effect. And if you can notice SERC East in particular, we noticed that there was kind of a reverse trend where typically we were seeing like the red bars higher than the lighter blue ones, except for SERC East. And what that told us was SERC East was more sensitive to weather, whereas other subregions were more sensitive to outages. And that was something just to think about. Interestingly enough, we completed our study just before Winter Storm Elliott, and while the assumptions weren't the same, there were some very insightful takeaways from it. So to summarize, we are sharing our experience so that others might benefit, those looking to perform probabilistic assessments, but also those looking to read reports and see what can we take away from this. It's important to also consider the practicality of what assumptions and data goes into it, knowing that we'll never have perfect modeling capability or perfect data. A question I often get is, how do we use historical weather data sets to predict the future? And maybe just one interim solution like we used is by either increasing the frequency of occurrence of certain extreme events or increasing the intensity of them. I also want to highlight that our stakeholders definitely saw the benefit of a region-wide model in supplement to what they already perform. And while we might lose some granularity of those, there is still a lot of insight to be gained from the region-wide modeling. That's all I had. Thank you.
Thank you, Anaisha. And I think on that last point is a good transition to our last speaker, Ralph Pfeiffer, who is joining us from Europe, from Germany specifically, where he is the head of national and European grid planning processes at Amprion in Germany. And so on that last point, in Europe, they have a pan-European approach that's more coordinated across the European footprint so that there's explicit representation of how your neighbors are interacting with each other. And so I think that last point, Anaisha, that you made on the regional modeling and showing how there's benefit in kind of seeing across the full SERC footprint is a good transition to Ralph and talking about the European approach. So hold on, everyone. We got one more speaker. We're almost there. Everyone's doing great. So thanks for bearing with us.
So, issue solved. So, yeah, I know I have the challenge here of maintaining your attention for the last presentation after a long day. I would try to do so by bringing in some European flavor, and I see I have support from the weather, so nobody is going to escape right now, I guess. So that could be helpful in this case. So I'm talking here to you today here on behalf of NCE, the European Association of Transmission System Operators, which is in charge of this European Resource Adequacy Assessment. And myself and my colleague Marlene Petz from Austrian Power Grid, we are both, let's say, sharing the steering group of this project, which I would like to acquaint you with. So a little bit of background information. What is the ERAA, the European Resource Adequacy Assessment? And the answer on this, what it is also an answer, a strikingly surprising answer on the often asked question: how can you bring together so many TSOs to do a European-wide study with 27 member states and some more? Simple answer is it's a legal mandate. It's a legal mandate by European legislation, which forces us working together in this domain. Not sure whether we would do this in a similar way voluntarily. So what is the ERAA? It's a pan-European assessment monitoring of the power system resource adequacy. It shall happen every year, so it's an annual process and gives an outlook on the development of the resource adequacy for the next 10 years. This legislation is in place since 2021, so we are now with the recently released 2023 edition is a third one. This is currently still under scrutiny of ESA, the Agency for the Cooperation of the European Energy Regulators, which shall approve the ERAA. And we are very confident to get an approval in the next few weeks there. But as of today, ESA is still working on it. The objective is of this ERAA is to inform policymakers, decision makers on the development of resource adequacy, that they also can take informed decisions on where in cases where resource adequacy is concerned, identified, what could be the appropriate mitigating measures like capacity mechanisms in the member states and so on. This chart gives an overview on how the ERAA works, the entire product. You have to read it from the left to the right. It starts with a data collection from all TSOs and also from the national energy plans, energy and climate plans. All these data are collected by NCE and fed into the NCE databases on generation capacities, all relevant information about renewable developments, demand developments, and also relevant information on the European internal market, which is for the entire Europe, separated in a larger number of bidding zones. Each bidding zone from a network or grid perspective is a couple plate, but then of course they are connected to each other by transfer capacities for power exchange between the bidding zones. Typically one bidding zone covers one member states, but some have introduced also internal bidding zones, so there's a bit more granularity on this. Based on this with this database, the computations consist of two main steps. First step is to do an economic viability assessment, which is investment modeling to decide on the generation portfolios to deliver results on the optimal generation storage portfolio, as well as demand side flexibilities. With the outcomes of this economic viability assessment, then the adequacy simulations start, which is a probabilistic analysis based on an economic dispatch model or production cost modeling, as you call it here. And the outcome of that second step then is indeed the metrics and relevant data about the resource adequacy. We have as relevant adequacy criteria here in place LOLA and energy not served. Just to mention, European definition of LOLA is different from the one used in North America. Typically, or I guess what you would call loss of load hours equals the European definition of loss of load expectations, just to be aware of that. This year's edition of ERA has covered or is covering 4 target years in the next 10 years horizon, 2025, 2028, 2030, and 2033. And the probabilistic approach is based on a combination then of 35 climate years and 15 forced outage pattern, resulting in 525 Monte Carlo simulations in the adequacy part. But before we come to adequacy, we have to do the investment modeling first, the EVA. And I will, in the following slides, dig a bit deeper into how this EVA methodology works, actually. The input you need there is about which technologies, which assets are subject to an economic viability assessment. This covers all nuclear or all thermal generators, but also batteries, new gas-fired or hydrogen ready generation capacities, as well as demand-side flexibilities as expansion candidates, and the corresponding techno-economic parameters are also needed. So some financial data for the modeling, like capex, risk premiums, hurdle rates, but also the different costs and prices typically needed for investment modeling. All of this together is put into the model with the characteristic as given here in the slides, and as an outcome, you get then the changes in the portfolio compared to the input data which were collected from the TSOs. We currently use the so-called overall cost minimization approach for this investment modeling, which consists of a single objective function covering all target years together. There's one big optimization problem, and this target function or objective function, I will not now explain the single variables, but the 3 categories you can read here: the build cost, the fixed operation, the maintenance cost, and the variable production and costs of unserved energy from the objective function. Having said that it is a single large optimization problem, this investment modeling, the computational challenges are huge and need some simplification. This simplification is done by clustering the climate years. As said, we had the input of 35 climate years, so we cluster them by some clustering methodologies, not to be explained here in this short presentation. but the outcomes are 3 clusters, and each of the cluster of climate years is then represented by 1 climate years, which is a way and which has a weight to replicate its occurrence. So we have used in this era 2 different scenarios, which are distinguished from each other by the weighting of the climate years in the clusters. There's so-called scenario A, where the clustering and the weighting factors try to replicate the average lowly we had in the last year's edition of the ERA. That was something done upon request on the regulators, ACER authority. And the second scenario is a clustering which represents the probability of occurrence of each climate year in the clusters. So that was a brief sketch of the investment modeling. The economic dispatch modeling for the adequacy analysis is typical, as said already, Monte Carlo simulation, where we combine the time series for each climate years made of wind, PV, and so on, and demand time series with the outage patterns, and conclude then in this 525 Monte Carlo years to be investigated. And the adequacy matrix, which values are concluded then from the adequacy runs are the loss of load expectation and the energy not served or expected unused energy as defined here. So coming to some outcomes of this year's calculation, we start with the EVA. So here on the slide, you see a number of bars, and I guess I have to explain a little bit because it's you cannot really read what each bar is made of. So actually, each target here for each scenario is represented by 3 bars here. The left bar is the input to the investment model. So the generation portfolio, battery portfolio, demand side responses, which goes in there. Then the left bar for each target year and scenario is the outcome of the EVA, and the middle one is the net effect from the investment modeling. And you can observe here that for almost all target years in both scenarios, the investment model calculations result in a net decrease of German generation capacity in Europe. Only the scenario A shows a slight increase or net increase in 2023 under scenario A, which is mainly driven by investment in gas generation capacity, with hydrogen readiness in Germany. So that with that outcome of the investment, we do the adequacy calculations, and the adequacy results in terms of lowly are then compared against nationally defined reliability standards. Here you see a selection, or you see not a selection. This is all reliability standards we have for the moment in Europe. So not each state or each member state has defined a reliability standard yet, and they diverge between the member states who have defined something already. So there's no uniform reliability standard in Europe, across Europe, but this diverges nationally. Here now you will see a couple of very similar slides. Now are the results of the adequacy runs, which are given here for each target year for both scenarios. Starting with on the left-hand side here of the slide with the target year 2025. And what you can see here are some blue bubbles for each bidding zone of the European market. It coincides with a member state or a state where we have only one bidding zone within a state, or we have several ones like for Scandinavia or Italy, which is divided in further zones. And for each of the zones, the blue dot indicates the lower value. Figures are given in there, the bigger, the higher. And the red dot added here to some of the member states indicates those for which countries which have a defined reliability standard where it is exceeded. And from the sequence now over the target years, you can observe that resource adequacy concerns increase in Europe. Simply by seeing that on the right-hand side for the target year 2028, you already can observe more red dots here to more member states, and the blue bubbles tend to increase often. And this trend continues then for the subsequent target years of 2030 and 2033. So in total, we expect increasingly adequacy concerns throughout Europe in more countries, and they become more severe in terms of the number of the LOLA hours expected. So the same exercise for the other scenario, comparing the two scenarios against each other. You see that you have in the scenario B here more in general higher LOLA values than compared to the scenario A, but the trend over the target years from 2025 to 2028 and then 2030, 2033 is the same. It increases simply. So the LOLA values become higher, and the number of countries as well where the defined reliability standards are exceeded. So putting a spotlight on Germany, this summarizes what was maybe a bit hidden also in the previous charts, and shows that now here you can see for each target year and each scenario the LOLA values and compared to the reliability standard. And the conclusion is also quite simple, that in almost all scenarios, Germany will not be able to meet its reliability standard. And that is then a so-called resource adequate concern and should motivate the German federal government to do something against it. This is what to do against it, what are the possible mitigation measures is currently still under controversial political debate in Germany. But what is already on its way is that we will introduce a kind of capacity mechanism in terms of a power station strategy, or so we call it, where the core element is to build up to 10 gigawatts of hydrogen-ready gas generation capacity by 2030. 10 gigawatts actually from is 10 gigawatts less than needed. So actually what we would need only in Germany to be able to meet our reliability standard in all target years would be 20 gigawatts, if not even more. Another slide I would like to show you about the LOLA results for the target years is that LOLA value only, as it is an average, tends to possibly underestimate what are the real concerns. This goes into the direction of tail events. And here you can see, besides the LOLA value, for each member state of the European Union, also the so-called loss of load duration in terms of the 50% percentile and 95% percentile, which equals to a 1 in 20 years event. So the blue bar for each member state is the average LOLA. The orange one is the 50th percentile for loss of load duration, and the gray bar is a 29th percentile for a 1 in 20 years event. And you see that even with a low, very low average LOLA, you can still expect, or would have to expect, there's a risk of long duration of adequacy shortfalls in many or most of the member states. So that was a quick rush through the ERA product and its results, and what are the key takeaways from it. We see that over the next years, fossil fuel capacity is at risk. High volumes of thermal generation capacity in Europe are becoming economically non-viable and will be decommissioned. And the results will be increasing adequacy concerns and teasing adequacy risk, and which call for corresponding mitigation measures, countermeasures to be taken. Regional coordination is of utmost importance, because whatever you do in a single member state in Europe, because of the interconnected transmission system, has an impact on the neighbors. So, for example, if Germany invests and establishes 10 or 20 gigawatts of needed generation capacity, that will also have an impact on the resource adequacy level in France or Belgium or elsewhere, and vice versa, of course, as well. If France does something, it has an impact on Germany. So it may be a kind of a Mikado problem, then who moves first to solve adequacy issues. That is are the main issues to look at. And last slide now with the outlook on what will happen in the future, since ERA is an annual cycle. Though 2023 edition is still in its final stage of approval by ESIG, we are already working on the next edition. We are preparing the 2024 ERA, and we are still in a phase where from each ERA edition to the next one, we identified potentials for improvements in methodology and approaches there. And a number of questions is listed here, which are under discussion currently with an NSOE, but also in the so-called magic triangle, which is made of NSOE, the ACER as an authority of the regulators, and the European Commission as a legislative authority. For example, the very first one is strikingly simple, because we have to do it annually, and by legislation should not select 4 target years, but do it for every single year in the next year, in the next 10 years, in the next decade. And does it really make sense, or can we reduce the problem here, being realistic about what can be achieved and be solved computationally and also time-wise within the process that happens every year. What we heard also from other presentations, it may have added value and its benefits when you go for more sensitivities. That is under discussion. The mutual impact of the capacity mechanisms in the member states, what I briefly had explained to you, is it already sufficiently investigated and considered in the methodology? That is something to be reconsidered. Do the scenarios adequately respect national projections, or is a distinction needed between the objective of an ERA for a shorter term horizon? Because for the next 1, 2, 3 years, investment modeling does not make much sense, because any investment, new plant, takes time until it's built. So we have probably a different objective for the shorter term and the longer term, so the first 5 years or the second 5 years of the entire period. And this is maybe the most controversially debated, or will become the most controversially debated issue, is, does the economic viability assessment actually realistically reflect investors' decision-making for new builds and retirements? And we expect some very interesting discussions there, in particular with ACER, about the methodology. So that's all in a nutshell about this European product here, which I would call, and I would be self-confident enough to call this cutting edge or world leading, not from methodology perspective, but from the coverage and the resources needed to bring 40 TSOs on to the table, to have the computational resources available. And so that is something I do not know whether this happens somewhere else in the world. And this is a great achievement already so far. Thank you very much for your attention.